Steady push on the piston causes a flow rate of 0.15 cubic centimeters per second through the needle. The fluid has a density of 900 kilograms per cubic meter and a viscosity of 0.002 kilograms per meter second. What force is required to maintain the flow? So let's take a look at this, and the first thing is, let's just quickly write down what we know. And so I know the density is 900 kilograms per cubic meter. I have a flow rate of 0.15 centimeters per second, and I have a viscosity of 0.002 kilograms meter second. So I look at this, what am I trying to find? I need to find the force. As I look at that, I'm like, wow, how do I find force? The only equation that we've had so far with force has been linear momentum, but we need to remember, what is force? What is pressure? Pressure is a force density. And the way that we find pressure is force over the area. So, if I take my pressure, multiply it by the area, that will give me the force. So what I need to do is I need to find the difference in pressure, which will give me the pressure that I'm pushing on, multiplied by the area, and that will give me the force that I'm looking for. So I'm going to need to go and use my energy equation to calculate out exactly what my force is. So as I take a look at this, what do I need to do? Well, I'm going to draw my control volume. The way I'm going to control my control volume is I'm going to do it right here at the exit, because I know what the flow rate at that point is. And so I'll be able to calculate out the velocity. Now I'm going to stop my control volume and not go all the way to the needle. I'm staying far enough away from this plunger pushing in so I don't have to worry about a deformable control volume. So I'm going to assume that, much like the surface of a large tank, we really don't have a lot of motion going on in the middle of this needle. So let's make our assumptions, because I do want to use the energy equation. I have the fixed CV, I have the one-dimensional inlets and outlets, which I am going to make those assumptions because we're going to use the conservation of mass. And even if we didn't need these for the equation, they're still true. Inlet, outlet. I mean, whether or not we use these assumptions, they're still true assumptions for our situation. So the third thing is it's a steady flow. Even in the problem, it tells us that it's required to maintain the flow, so we're staying steady, we're not changing with time. Our fourth one is we're going to assume a constant density, an incompressible fluid. I'm going to assume that because I have some liquid. And I am going to assume that temperature is constant. There's nothing in here that says that it's not, and I want to be able to apply the energy equation. So let's write out our energy equation, and then we'll start knocking out terms and figuring out what to do. So we're going to call this point 1. We'll call this point 2. So we've got our inlet, then our outlet. And actually, because of the way that we write our equations, let's flip those and say that's 1 and 2, so nobody gets confused. So pressure over gamma plus V squared over 2G plus Z at point 1, that's our input, is equal to everything that comes out on the other side, which for the fluid properties will be the exact same at point 2, plus whatever head that we have from the turbine, minus whatever head we have from the pump, plus whatever loss due to friction that we have. Now, let's go through and knock out the low-hanging fruit. And when I talk about low-hanging fruit, I'm just like the stuff that's going to fall out, like right here. There's no turbine, no pump. They fall away. Z, we've got everything pretty much on a horizontal level, so we'll just say Z1 is equal to Z2. They'll fall out because they're not trying to push up or down. They're just zero. They're just at the same level. And the last thing, like I said, the reason that we drew our control volume to here is we're treating that kind of like the surface of a large tank because there's very little amount of velocity going through there. And so what we're going to do is we're going to say V1 is 0 because of that assumption of basically a large tank. So at this point, we're going to now write this down. I'm going to bring it over to the other side. I'm going to subtract over the P2 because I want to isolate everything that's going on. So I'm going to bring that over. I've got P1 minus P2, all of that over gamma. is going to be equal to whatever's left because I have nothing to move over to the other side. So what we have is V2 squared over 2G plus head loss due to friction. So the next thing we need to do is we need to figure out what the head loss is. And to do that, and we also need to figure out what our velocity is. So what we're going to do is we're going to take a look at things and go, okay, well, velocity, I know what my flow rate is, Q. And I know that if I divide Q by area, I will get my velocity. Because the definition's Q is equal to V times A. So let's do that. We have our flow rate, 0.15 cubic centimeters per second. I'm going to divide it by my area, pi over 4 times 0.25 millimeters. We're going to have to square that. Now, these units do not match up, and we want to get this into standard units. And for right now, let's just put it into, you could do centimeters per second squared, but let's just go right to our meters per second. So how do I do that? I have 1 meter is 100 centimeters, and I will cube that. And down here I've got 1 meter is 1,000 millimeters, and I'm going to square that. So if I go and I calculate that out, what do I end up getting? I will get 3.06 meters per second is my velocity. Okay, now that I have a velocity, what you need to do is figure out the Reynolds number and hope it's laminar so we can calculate out the head loss. So the Reynolds number is, let me change the color back to blue. Our Reynolds number based on diameter is going to be VD over nu, but we do not have those properties of the fluid. We have the density and viscosity, so we have to remember that we can also use VD rho over mu. So if I plug those in, I have a density of 900 kilograms per cubic meter. I have a velocity of 3.06 meters per second, 6 meters per second, and then I have my diameter, 0.25 millimeters, which we will have to get rid of our, move my pic. Oh, I can't move the picture. So, but we're going to multiply that by 1 meter over 1,000 millimeters. That will give us our proper units on the top. And then on the bottom we have 0.002 kilograms per meter second. Those units will all cancel out. And this will give us a Reynolds number of 344. 344 is definitely laminar, which I'm happy about, because then that tells me that, okay, well, I can calculate out F for my laminar flow is going to be 64 divided by the Reynolds number, which is 344, which is a Reynolds number of 0.186. So now we can go, and we'll go back to our original equation that we wrote and solve it. So we had the pressure difference. So P1 minus P2 over gamma is going to be equal to the head loss. So our head loss is FL over P squared over 2G. Oh. FL over D, V squared over 2G. That is my calculation for my head loss. And then I'm going to add to that V squared over 2G. So if I rearrange this really quickly, just so I don't have to do everything constantly, and that's V squared over 2G plus FL over D plus 1. So V squared is 3.06 meters per second divided by 2 times 9.81 meters per second squared. Then we're going to multiply that by our head loss, or excuse me, our Darcy friction factor. We're going to multiply it by the length that we have, and that's basically our just little pipe right there. So 1.5 centimeters, and then 100 1 meter is 100 centimeters. Divide that by our diameter, 0.25 millimeters. Multiply that by 1 meter is 1,000 millimeters. And it'll be plus 1. So we're running out of room there. Now if we go and multiply all that out, delta P over gamma is going to be 5.8 meters. So now if I multiply through by my specific weight, so I can get delta P, that will be 5.8 meters. Specific weight, remember, is gravity times density, so 900 kilograms per cubic meter. And then I'm going to multiply that by 9.81 meters per second squared, which gives us a pressure difference of 51.25 kilopascals, or 51,250 pascals. So the last thing that we've got is to calculate out our force. So we go back to our equation. Pressure is equal to force times area. So the force is going to be the pressure difference times the area. So here's our force. Our pressure difference is 51.25 times 10 to the third pascals. And then we multiply it by our area. So our area is pi over 4 times the 0.25 millimeters. Now we have to, squared. Now we're going to have to convert that into the unit of meter. So then we'll do 1 meter divided by 1,000 millimeters, and that will get our units correctly, and we'll make sure to square that. And so then once we do that, we're going to get an answer of newtons, because Pascal is a newton per meter squared. We're going to have meters squared as the area, so I'm left with newtons. So you're looking at an answer that's just about 4.0 newtons of force to maintain that steady flow.